because that's important these days. It's quite good at this. The end goal of sort of open source project is to make a fully sort of standalone 3D application. Bit of emphasis on writing and rendering. That's obviously quite an ambitious goal. So the aim is to use as much as possible out of really, really good open source projects that are out there. So elements using OpenCore.io and Moodle.io and genuine OpenCore.io. And the idea is just to keep adding more and more. So the standalone application you can download from GitHub now. It does a fair amount of stuff, but it's not quite there yet. So it can overland files, of course I've seen caches, and it's got nodes for managing your hierarchy, so you can merge things, counting lights, define what things, instance things. So it's got a reasonable tool set for building up the scene. It's got some basic nodes for compositing, based on OpenImage.io and OpenCore.io, and it also doubles as the framework for the rendering. So for the rendering backend, it supports 3D Live pretty well, using this IPL, and it supports Arnold reasonably well. That's sort of the prototype phase really. There's still a lot missing. So there's no manipulators, so you can't move things around the keyboard. There's no keyframe. Those are the obvious big gaping holes. The idea is to fill those in as we go on. But really, at Image Engine, we're using it as a framework. So mostly what we'll talk about today is how you can use the Gaffer framework to build tools. I'm going to do some really boring bits where I'm just trying to get across the basic ideas of the framework and how you might script it. And then these guys will fill in with more interesting sections about taking those ideas and building actual production-worthy tools. So I'm just going to do, bear with me, a little bit of talking about code before we get to some more pictures. So the core of everything's written in C++, so it's a bunch of libraries in C++ with Python writing. So there's pretty much a one-to-one mapping between C++ and the Python. So if you're comfortable scripting, you can script it and then move on to C++. If you tend to code in C++, if you want to rapidly prototype something, that's what I do. You can sort of move back and forwards. In practice, we code pretty much all the heavy lifting in C++, and the Python is just glue for the UI. But Python's a killer for performance, so I'm going to stick with C++. It's kind of modular, literally, in that plugins for the system are just Python modules, and applications just support the modules they want, and assemble them with config files to define them. I guess everyone knows what nodes and subs are, so we won't talk too much about that. I'm just going to start with a very little code example. Just to give you an idea that it's pretty easy to knock together a node graph to represent something and then build a UI around it. So we start with a script node, which is like the root of a file, basically. And it's called a script node because literally when it's saved out, it just is a Python script. So you can also kind of learn the script language just by reading files. So it's adding a node to the script. And then we can add some plugs to the node using Python dictionary syntax, so it's sort of fairly precise. Here we store an integer. And then we can set some connections between nodes. Then we might want to visualize that. So we make a window. We use Python's with syntax so that the indentation in the code matches the structure of the UI. So we can see that there's a split container inside the window, and then a node graph and a node editor. And obviously when we connect the nodes together, we can say how they're related spatially. So we can just use an automated layout algorithm to position them. And that gives us this little thing, a handy little guide to the British monarchy, family tree of our latest prince. So obviously not particularly relevant to visual effects, but gives you a bit of an idea that you can quite quickly build an application that kind of has a bunch of features and it's very little code. Like that was literally all the code we needed. This is really an example of using those to represent entities and the connections between them, which is kind of what we do with our asset management system, which Andrew will now talk about.
So we have a proprietary asset management system called Gucko. It's been around for quite a few years now, but it went through a major redevelopment a few years back based on the Gaffer framework. The link down there at the bottom is to a paper that was in DigiPro last year, where we talk a bit more in depth about this sort of stuff and how Yuka works. I'm going to go through it really quickly, just not to take too much time. I'm not actually like a main developer on Yuka. These guys sitting right here are, but they do want to talk. So I'll point them out anyway. So yeah, it's built on the Gaffer framework. It's a Python API and a Qt interface, and a lot of custom UI on top of Gaffer as well. But yeah, one of the key features compared to the original version is that new features to Yuka rarely affect the database structure, so it's pretty stable in terms of interacting with the database. I just listed a bunch of shows here in my notes that this has been used on. So we just finished Ninja Turtles. We're working on Chappie now, because we saw Elysium, RPD, 0-30, Fast and Furious 6, White House Down, Monster Hunter, and Child 44. So it's been through a lot of productions and improved along the way. So everything in Yuka derives from this one class called parameterize, which is in Cortex. That's like a base class. It just means like I have some parameters basically. And then Yuka has versionable entities and entities that store things on disk. And assets are built through a collection of connectable components, which are represented as Gaffer nodes. And then we also have libraries, which is a collection of assets. Again, there's more details in the paper if you want to know more about this stuff. So kind of the primary advantage of these connectable components is that we get things like automated compatibility tracking and data management. We can track things a lot better. So here's like a little picture of a graph. It's kind of hard to see in this room, but it is the final render. And then there's like a rig and a camera and a light rig and a model and a data cache. And specific versions of all those entities that we know went into making the final render. And you can just track it back through the graph and figure those sorts of things out and maybe automate some processes based on that information. So obviously a key component of asset management is data flow between departments. So we kind of have this concept of actions that are per role. So someone would set themselves as being a look they've already set the time or a rigger at the time, and then kind of the default actions get suited to that role automatically. And they all have similar like check out this asset, publish it, or just get it but not check it out so someone else can work on it at the same time. And all those actions are using UI code from Gaffer to present dialogue to the user with the various parameters that are necessary. So this is comparing two versions of an animation, kind of showing the difference between the versions. So he's going and selecting version 6 and version 2, comparing them. And then it's this little diff UI that's showing like a bunch of hierarchy changes that were made, but it might also be showing like class size differences and things like that. And then he's popping over in a little preview window, which uses a bunch of Gaffer components on the scene. And kind of colors the meshes, match the diff colors, and updates the sync selection between the two windows. Anyway, so there's a little overlay where one of the animations had the door opening and the wheels turning, and the other one did, and there's a sharp on top of something. And yeah, so it's kind of just this is on the Yuka UI, but we're not in any application at the moment other than Yuka. But if we were in Maya, we might be able to bring that into Maya, like my other video would have shown you. And yeah, it's kind of got the extra scene inspection UIs that come with Gaffer as well, showing there, and kind of different variable and assignment and transforms and bounds and stuff. And then just kind of just showing you, oh, this really is just a Gaffer graph. If I expose that to you, so you can hit the little G button and get the full graph pop up, and then go from there. And now you're the standalone Gaffer application at this point. If you want to do more complex things. So yeah, for our latest note shows, we added a concept called bundles as well, which is a collection of associated versions. So like we had different departments. And kind of the goal of this was to have one button updates for each department. And you can do some sort of automation for quality control renders and videos and things, and then do automatic approvals and automatic publishes based on that as well. This is just the last little note to say it was highly configurable. So we have technologies and advanced artists and things can register their own custom actions or their own little UI icons that have custom actions associated with them.
I'm a shader writer at Image Engine, and one of the first places where we've been using some of the starting to move towards scene assembly and Gaffer was for look dev and putting together shader networks. So this happened at the same time as doing a general switch to more physically plausible shading and more complex layering and supporting a bunch of stuff like that. That would kind of be a different talk, but I'm just going to talk a bit about how we use Gaffer to allow that. This is going to be a video of showing a random large network and just wandering around doing some shader stuff. It's a shader system that sort of does all the things you'd expect of a modern shading system. So this is just a large production network. Lots of nodes put together, lots of different DRDF components to layer, lots of layers for shader. And we can wander around the node network. We can look at different components. There's a little quick IPR preview of what the different components look like. So kind of just all the standard stuff, but it worked fairly well, and we had a very nice system for putting together all these components and quickly getting these UIs built, which is good because we fairly rapidly rewrote every shader in the building. Let's see. I don't think there's a whole lot else that goes on in this video, but yeah, lots of tweaking little shader parameters and that sort of thing. This is looking at one shader setup. We've got a simple little material with views and two speculators on top. You can see some little nodes plugged into the weight on the specular and things like that. So we can't see this code at all, but I'll just talk a bit about it anyways. In terms of what it takes to actually set up one of these little UIs, we just have annotations inside all our shaders that drive all the UIs. So the shader is a completely self-contained file. While you're writing the shader, you can just add little UI definitions there. My favorite part is there's a little reload button up in the top right that reloads the UI definition without exiting, so I can be in the middle of a complex production scene and be completely dynamic reloading all my shader code while I'm working on it. It makes it very nice to make quick changes. Yeah, we've got some annotations to set up some drop-down menus, set up checkboxes. We can enable and disable parameters, and then all these other parameters, set up dividers, and drop-down subdivisions to organize things. So yeah, basic stuff, but sort of makes the simple stuff simple. And then it ends up looking like some code like this in the rib, where we output as co-shaders, pass that off to the renderer. There's a lot of low-level problems with how we interface with the renderer, where this isn't necessarily the best way of doing shaders, to use co-shaders this way. That's a different topic, and we're looking at different ways we'll approach that in the future. If anyone wants to hear gory details, they can come talk to me. But the Gaffer side of things has been working really well in the system. Got that. Yeah. So yeah, we're now making much more complicated shaders than we were before. I may be putting words in people's mouths here to say that the artists are happy. I guess Matthias and Judith can call me out on it afterwards, but it seems to be going a lot better than it was before anyways. So yeah, we've had a fair bit of success rolling this out to look dev, but at the moment our main focus is going to be starting to roll it more out into lighting, which is going to involve some other stuff that Don's going to be talking about now.
So far, in your Buka and the shader graphs, we've just been using node networks to represent sort of entities and the relationships between them, but there's no actual data flow through these graphs. For doing things like scene processing and image processing, we actually need to compute stuff. So we're now going to talk about the Computation Framework in Gaffer, which sits on top of the basic node framework. And there's going to be a bit more code. This is all the code for a simple code. There's not too much code involved really. It's derived from the compute node, which sort of puts some requirements on us. We have to implement the methods below that you can see. We have a few input books, just like we did before, and when we're adding an output book here, it's going to be our responsibility to compute the output value for this anytime it's needed, which we do in this method. This is just a node which just outputs a sine wave, depending on time. So we can get simple values from the plugs, and then there's this context thing where we get the frame. Contexts are quite important for threading, we'll come to that shortly, but for now we just need to know that we can get the current frame out there. And we have to implement this hash. Do a bit like sort of cheap compute that just comes up with a signature, sort of unique signature for the result, and that is used for the caching system, so we can avoid recomputation when we don't need to do it. It's a bit of a gory detail, which can sort of gloss over that from now on. So that would just be context that frame, sine alpha, that's what I have here. So I said that contexts are quite important part of this framework, and they're actually the key to doing multi-threading in Gaffer. And the way this works is they provide external information to the graph computation. So the graph's actually a static entity, it can't change over time or without going to sort of output. But the context provides varying information from the outside that allows that. So we can compute the same node in different contexts. So this is just a simple setup that says I want to compute the frame 10 and then pulls on the output book. You can do this for multiple threads, so multiple threads can ask the same question at different times, and that will all run in parallel. And the whole graph is evaluated in that thread rather than being threaded per node. Being able to do that at different points in time isn't all that useful, but when we come to image processing and scene processing, we'll use other entries in the context which allow us to thread the computation for those things. And those can also change the current context during compute, so that's how a time warp would work. It would push a new context, changes the time, and then put on its inputs. So when you change the context like that, the contexts are flying up the graph while the data's flying down. And this lets us do quite a bunch of things. So for images, we can sort of break the image down into having a display window, which is the full size of the image, the data window, which is where there's actually useful information. The channel names we have, and floating point data per channel, per pixel. Which is basically just the way OpenEXR represents images. And then we represent this in Gaffer with a compound plug, which is a plug with children. And there's a child for each of those things, so each of those things can be computed individually. And that makes sense for the display window and the data window of the channel names, because computing those is super quick. But it doesn't make any sense for the channel data, because we don't want to compute that in one huge chunk. Because we're slow, we can't thread it, we might not want all the data anyway. So that's a bit of a problem. So naturally you just break things down. So we break things down into tiles within channels, and then we simply just specify which tile and which channel we want in a context. So we just put entries into the context as if it's a dictionary saying we want the red channel and the bottom left tile, and then we spawn on the book. And that'll give us the data for just that tile. And then by spawning a bunch of different threads, we can pull in multiple tiles in parallel. So this is the way the viewer works. It just spawns threads and processes tiles into the sky everything it wants. The nodes themselves aren't doing any threading. They're just, they have to be thread safe, and then it's up to the sort of observer of the graph to use threads as they want. And for 3D scenes, we have a sort of similar bunch of requirements to images really. We want to be able to use the graph to do sort of non-destructive procedural editing. And the amount of work we want to do is potentially very large, so we want to be able to do it in individual chunks. Specifically, we want to be able to access random parts of the hierarchy in compute base. So then the question is, how can we do that within the little framework we've got so far? Just a little example showing what standalone Gaffer shows. We've just got a very simple node network grouping a sphere and a plane. And we can see that this results in a very simple hierarchy. And if you think the group has the property that it has two children, and then the plane and the sphere have no children. And And in the scene inspector, we can see that the plane has the following properties. It's got a transform, a bounding box. It's got some attributes, which is just an arbitrary list of sort of beta, which applies to it. In this case, it's the random shading rate, but you can put anything you want in there. And then it can have an object as well, so there's a mesh in there accessing the plane. So at any location in the hierarchy, you can store these things. So in the same way we broke things down into a compound flow with specific children for the images, we do the same for scenes. So there's a flow for the bounding box, for the transform, for the attributes, for the object, and for the child names. And we use the context to specify which location we're interested in when we're doing the compute. So we simply set up that we're interested in the group, the plane underneath the group, and then set that as the current context, and then pull to get the transform and the mesh. So we can compute any location in the scene and any of those subflows as a distinct unit, and we can thread that in any way we want. In practice, the viewer spawns all the threads which manage a traversal of the graph until they've got the whole thing, and when we're rendering, it's up to the renderer to call procedurals as a C-step. So we do a tree of procedurals, and the renderer will expand when it wants to. But the point is, the graph is ready to accept any query at any time, and that can be done in parallel. So the entire graph computation is in parallel. So that's kind of the theory of it, and then David will sort of take you through how we're actually using that to do lighting and rendering in production.
So this is a system called Caribou. It's for pulling data from applications like Maya through Gaffer, so it can be processed afterwards. So it's one of the foundations of it is this scene interface class, which is a abstraction of a 3D scene. So you can potentially write a scene interface implementation in the lambda file, for example, or our scene cache files, just to highlight the data format. And we can also do this for live scenes, like Maya and Houdini, have context of these things updated and applied. So some of the current applications of this are so those are our scene cache nodes, like a nice way of just boxing up big geometry hierarchy, so you don't have to have millions of line nodes floating around. And you can also crack them open, like you can see in the demonstration there, and actually access the individual components and move them around and stuff like that. There's also a feature where you can just turn them into live geometry if you want to actually edit vertices and things like that. Animated and stuff like that as well. Yeah. Right. Yeah, so which leads me into this Caribou system. Leads me into this Caribou system. Previous, image engine kind of started out with character work, so we've been using all these isolated render time procedurals, which were pretty good for putting together individual characters, but started to cause problems as our scenes got bigger and bigger, so you couldn't really share shaders between these procedurals particularly easily. So I experimented a bit on our recent Ninja Turtles show with having a Gaffer graph that kind of just floated around in Maya scene, and we applied to these render time procedurals, so you can do things like filtered shader assignments on them, and that seemed to work pretty well. It seemed to save us quite a bit of headaches, and we actually did a smaller show almost entirely in that system, so Caribou is kind of taking that a little bit further. What it does is, you bring your geometry and using these Maya scene shapes, and a scene kind of gets sucked through Gaffer. Gaffer interprets these scene shapes as extensions to the Maya scene hierarchy. It also pushes lights into it. It's built on top of this scene interface thing, so we've got a scene interface for the live Maya scene, which a Gaffer node is operating on. Gaffer takes over the Maya scene, do shader assignments, render pass management, do IPR as well. So yeah, hopefully I'll be able to take you through with this and narrate it. This is Maya with a bunch of Gaffer panels integrated into it. So it's got a fairly simple geometry at the moment. It's like Spirit of playing. You see the scene input node up there. This is how it makes it into the Gaffer graph to start with, and the selection is synchronized. And also, if I start moving things around, you can see that it updates the Gaffer as well, and edit vertices and that kind of stuff. So yeah, what I've done here is a bit of pass management. I've got a beauty pass there, which has got a diffuse shader on it, which you can see in the live shader preview over there. Just kind of tweaking the parameter. And then I've got another pass which is just a matte pass, and that's got a constant shader on it. So very regular. Alright. So now in addition to live model geometry, we'll import the caches. What's that one? Yeah. There we go. No, anything a shot. So yeah, I'll fire up the IPR. This is free to light, but really interactively. So you can see you can move the camera around. You can also move the lights around, adjust the violet light there. You can, in a bit, hopefully you'll be able to move objects around as well. It's visually nice to do that. So now we're going to import some shaders from our asset management system. So I'll put the human character, the shark, use now an obsidian terminator. So yeah, I've got two boxes that are coming there, and the approach that I'm currently taking is that they're scoped. So you can see that little scope, just about scope parameter there. It's targeted at the shark, which means that the contents of the box can only see the shark, and all the parts that are referred to inside the box are rooted at the shark. And there's also some pass multiplexing going on, so you can see I've set up two pass streams there. It's like a beauty pass on the left and a matte pass on the right. So I'll just go and fiddle with one of the shaders in the beauty pass. Not that the number sharp is a bit high frequency, so I'll turn it down. Or realistic. So there we go. Beautiful. Should be a little bit like this. And okay, so yeah, I'll just show you what the matte pass looks like. And I sort of pull through all the shader assignments on the right side of the graph, so inside the box to the left. Okay, sharp. So yeah, another thing that you can use this system for is procedural geometry. We've been working on some first stuff using Gaffer nodes. So I'm just going to show you that. Yeah, I'm just pinning it to my viewport there so you can actually see a bit of feedback in the viewport. So you can, I'm going to edit a little guide curve in the back of this head and you're going to be able to see that. So yeah, there are first system nodes. There's like a seeder which generates hair follicles and a grower which generates curves. And then there's a guide curve. And then it's like, so I'm expanding the hierarchy a little bit so I can actually get to the guide curve and edit it. Just to turn it into actual editable geometry, you know? So, yeah, the contents of that box are switched with this scene switch node. It's actually switching, it's just putting through the input at the moment. But I'll change that index parameter to pull through on the hair system branch. It's exposed on the top of the box. You'll be able to see he's now Christopher Walken. There you go. And yeah, so you can, I'm just going to grab the curve and do a bit of editing on it. I'll just show you the IPR of that. So that's good. This is using a shader that Daniel mocked up for us using 3D Light's new air performance sampling stuff, which is really based on the technology we use on videos. Well, so yeah, another thing I managed to do is we've got a basic feather system working inside there, so I'm just flipped the switch and activated that, and it's like growing golden worms on his head.
So yeah, I hope that was clear there, but like Gaffer's running in my there, it's not like two applications talking to each other over a port or something, it's seamless, it's on the same Qt thread.
Yeah, I forgot to say actually, like the undo queues are synchronized as well.
Queues are synced as well as a selection. And yeah, he's overlaying Gaffer geometry onto the live viewport as well. Okay, so now I'm going to talk a little bit about the Dispatcher framework just very briefly. So this is kind of like David's got it set up. There's this math pass, there's this beauty pass, but how do you render these other than the IPR? So in Gaffer, there's this concept of executable nodes. These are nodes that have some sort of external side effect, like file creations, like an image writer or a render node for any of the renderers, or a scene capture, or underground or something like that. So every executable node kind of defines, given this context, this is how I'm going to execute, and we call that a task. And then they also have inputs and outputs for requirements. You can put up a graph of executables and have dependencies between passes and comps and things like that. And then we have this other class called Dispatcher, which is responsible for managing all the executables. So it's going to process the requirement graph of executable nodes, generate and execute a task graph. And that's all done in the base class, like all that processing basically, and then each dispatcher implementation basically just gets a task graph and it knows it just has to traverse the tree and execute. So we ship a local dispatcher with Gaffer, so that will like render all your nodes in the processor in the background on the background thread. And just kind of, and then internally at Image Engine we have a farm dispatcher to talk to our render farm, but it's pretty easy to knock up. Like it's our farm dispatcher is a Python file that's maybe 100 lines. So it should be pretty easy to integrate into any render farm, I would hope. If it's not, you can talk to me about it and we can fix it, or you can fix it. So here's just my little stupid test scene. So here I'm like writing a cache file, so that's like an Olympic cache, but it's a scene cache. Here I have one render pass and another render pass, and then here I have one slap comp and another slap comp, and then I have a final comp that depends on those two. And so you just go to this node, hit the execute button, this UI pops up, and these are the parameters for the local dispatcher, or here you can switch to any other dispatcher you've registered and get its parameters. And dispatchers can also register like per node parameters, so this is the dispatcher tab on each of these executable nodes. And here it's like these are the farm ones, so it's talking about like memory reservations and things you need to tell your render farm about. And then there's the local ones that are just like, it's kind of an override that says like force this one to be on in the foreground instead of the background if you need to do something synchronously. And there's a little batch parameter up here, so that's for clumping frames together. And we kind of expose that in two different ways. So like this node, since it's like an Olympic cache, you end up with one cache for your entire animation. It kind of like just implicitly knows I have to do all the frames at once in order. And then each of these render nodes, it's kind of down to the user to say like that's a super fast render, you might as well just do 10 at a time. Or that's a really slow one, do it one at a time. And then the dispatcher system should resolve all that for you and hand you a tree that's safe to traverse as you look. And now I'm just going to kind of do a quick status update and roadmap for where we're going with this. So yeah, in case you didn't catch it in the beginning, this is all on GitHub. We do all our Gaffer milestones and issue tracking publicly on GitHub. Every one of us on the image engine RD team has a GitHub account, and we're on there all the time, kind of discussing implementation ideas with each other and getting feedback about things. And yeah, GitHub is pretty good for that. We have code reviews. We all have our own forks. We're treating it basically like we're all external developers. So we all have our own forks. We work on our own branches. We put them up there for review, and someone other than yourself is responsible for reviewing it. Yeah, it's been working pretty well. So internally at Image Engine, we kind of this is currently what's driving the milestones on the Gaffer project because Image Engine is the only one paying any of us to do this. So that's cool. But we get to push Caribou along, which is the top priority at Image Engine right now in terms of Gaffer milestones. So we need to get the full render best management sorted out. It's coming together. Like David showed you some stuff, I just showed you some stuff. Just a few more things, and then that should be good. And then kind of the milestones we have John working on at the moment are to do with scene exploration and debugging. So it's like improving the scene inspector and scene hierarchy UI, so you can get some better heads-up feedback on what's happening in your graph. And he's put in a lot of stuff recently that we didn't show, which is pretty cool, like where in the hierarchy a shading attribute was set, which node set it, things like that. Another thing we want to push on the Ibuka side is this kind of idea of workflow graphs across applications. So how does a shot come together? There's like a model publish and a rig publish and an anim publish, and a lighting render and a lighting publish, and so on. Can we model that as a reproducible graph in Ibuka so that some sort of automated script can just re-trigger like my shot, basically. I got no like 3D my shot sort of thing. We also need some sort of paint system. We haven't decided exactly how we're going to do it, but in terms of like, everybody likes to paint textures for things, just for masks and whatever. And kind of some of the stuff you started to see in terms of like, we're putting hair on things and procedural generating geometry, and also leaves, and hey, why not crowds and environments and vegetation and things like that. So that's kind of what Image Engine is most interested in next for this. Outside of Image Engine, I think John kind of hit on the biggest obvious thing is manipulation tools. So currently Image Engine is using Maya for manipulation and sucking all the geometry in automatically, which is super cool, but you might want to actually move a camera or light around on your own in Gaffer, which would be cool too. More renderers would be very neat. OSL, John actually did a Gaffer presentation at the OSL off earlier today, which he can show you the slides for afterwards if you're interested, but he demonstrated using OSL as a deformer language, so deforming geometry rather than for shading, which was pretty cool. And that's all shipping with Gaffer right now. And then it's like, it'd be really cool if someone wanted to put OpenBDP support or bullet support. It'd be really interesting. So yeah, go grab a fork and play around and maybe contribute back. That'd be awesome. So I just wanted to acknowledge the entire R&D team at Image Engine, as well as ID management, and all the artists who make this actually worth doing. So here's the dev list. Again, we're on there pretty much every day. John answers questions pretty quick. So if you have a question, email it there. If you want to see more about demo scenes and things like that, user docs, that's this one. And this is code, and the binary releases on Linux and OS X.
This video was originally shown at FMX 2014 as part of the open source session on Cortex and Gaffer. We're demonstrating one use of the Gaffer framework as a look-dev lighting environment. Here we've taken the exploding droid from Elysium and reconstructed the look-dev inside of Gaffer. We didn't really do it this way on Elysium, we've just reconstructed it after the fact. We're exploring the complex droid hierarchy in the OpenGL viewport. We can expand using keyboard shortcuts in the viewport directly or using the scene hierarchy panel in the lower right corner. Boundary boxes in the viewport represent unexpanded hierarchy. That geometry is never loaded off of disk. Gaffer's caching mechanism speeds up repeat computation, which improves playback speed in the viewport. In this example, we're using the scene cache file format provided by Cortex, which computes accurate bounds as you write the cache. You could use Alembic instead, as long as you provide accurate bounds. Now we're demonstrating an interactive progressive render using 3-to-Light via Cortex. The Gaffer graph is actually a delayed load procedural evaluated at render time. We get pretty decent IPR speeds for such a complex production asset. This droid has 2 million polygons and approximately 150 gigabytes of textures. We can update shader settings on the fly. Here we're targeting the facing tint on a single 3-to-Light co-shader in the look-dev setup for the droid. As we update the parameter, we send edit requests to the 3-to-Light IPR render, and 3-to-Light resamples the image. We can also update light settings and transformation values on the fly. Here we're updating the tint on the environment light. Note that we're setting the transformation values directly in the node editor. We don't actually have interactive manipulators in the Gaffer viewport yet, though it's on our roadmap for the future. Since the scene is flowing through the graph, we can simply branch off for batch and preview rendering and have different render settings. The batch nodes are executable nodes, which can be sent to dispatchers. Currently we only have a local dispatcher, though we plan to have farm dispatchers in the future. Once our batch render finishes, we can slap it over the plate and toggle between the results. In the future, we'd also like to be able to send this slap comp to the farm, as well as a daily, all from the same Gaffer graph. Thanks for watching the video. If you're interested in getting involved in Gaffer, you can download the binaries on the GitHub page, or you can fork it for yourself and try it out.